So you asked how we know quarks and leptons are elementary particles rather than composite particles. And what I mean is elementary particles mean that they're the most fundamental version of the particle at the smallest scale, they're little points, whereas composite particles are made up of smaller particles. An example is the proton, which we once thought was elementary, but as we looked at it more closely, we found that the proton was actually made of smaller particles. So how do we know quarks and leptons aren't also made of smaller particles? And the answer is we don't know for sure, but we assume that they're elementary because we've never seen any evidence that they're composite. So if we look at the proton is held together by the strong nuclear force. And at low energies, the strong force is very strong. That's how it got its name. But as you increase the energy, this force actually gets weaker and weaker. And you can start to, here's just the proton, and then you see the quarks bound together by very strong gluons. And as you go to higher energy, this force gets weaker. And you can start to see the effects of the quarks that make up the proton. And we needed to reach an energy of about 1 GeV to see these effects for the proton. So it's possible that quarks and leptons are composite, but we need to go to even higher scales to see this. If they were composite, there's a number of ways we might discover them, but I'll give you 2 examples. So one way we could look to see if quarks and leptons are composite is to sort of try and bounce things off of them and see what happens. So if quarks and leptons are elementary, no matter how high energy we bounce off, we'll shoot things at them and they'll bounce out and we can sort of trace back where everything came from. It'll always look like a point. If quarks and leptons are composite, however, eventually we'll be able to bounce things off them at high enough energy that we can see that they look more like a blob. And as the particles scatter off, we can reconstruct where things came from and maybe resolve a bit of this blob picture. Another way that we could test to see if quarks and leptons are composite is that if quarks and leptons are composite, their ingredients are sort of bound together, kind of like a hydrogen atom. And the ingredients feel the force that's binding them together, and this force can look like a potential well. And so what we see now would be the electrons and the quarks would be in their ground state, but quantum particles in a well have excited states. And so it's possible that depending on the shape of this well, if we get to high enough energy, we could access one of these excited states. We've actually been looking for excited states for quarks and leptons, and we haven't found any. But we can say that at least up to a certain energy, we know there's no excited state. So for electrons, we've ruled out excited states up to 3,000 GeV. And for excited quarks, we've ruled out states up to 4,000 GeV. So up until these energies, we haven't seen excited states, but it's possible that this force is very strong, and this well is very, very steep, and this excited state exists at a very high energy. And we don't know. The only way to tell would be to look at higher energies. So to summarize, everything we've seen suggests that quarks and leptons are elementary, but it's certainly possible that they're composite, and we just can't see that because the scale at which we'd see the compositeness is a very high energy scale.